Missile defense isn't just about explosions. It's about split-second decisions, invisible networks, and machines that think faster than the enemy can react. In a world where threats travel faster than sound, these systems stand as silent guardians. But how are they made? From the spark of a military idea to the roar of a missile launch, we'll take you deep inside the factories, the control rooms, and the battlefields. You'll see how precision engineering, solid fuel technology, and AI-powered guidance come together to create the most advanced defense tools in modern warfare. This is the story of how missile defense systems are made, from idea to blueprint. Every missile defense system starts with a question: how do we stop what's coming? Whether it's defending a frontline battalion or shielding a city from aerial threats, that question drives everything. Planners and engineers gather, military minds thinking tactically, engineers thinking technically. The early stage is a mix of urgency and imagination. Threat assessments guide the mission type: intercept fast-moving ballistic missiles, defend against swarms of drones, or support mobile ground units with a fast reaction system. Sketches and drafts appear, mock-ups showing missile pods, launch vehicles, radar arrays. Then comes the balancing act: portability versus power. A larger system can carry bigger warheads or track more targets, but it needs heavy support vehicles and longer setup times. A smaller one can be quickly deployed, even by aircraft like the C-5 Galaxy, but may carry fewer missiles. Engineers weigh every trade-off, constantly asking, what matters most in battle? Next is platform selection. Some missiles launch from ground vehicles, others from planes or even ships. Systems like HIMARS offer fast, single-pod deployment, while MLRS platforms can carry more but move slower. Each choice maps directly back to battlefield strategy. Naming conventions often follow function and origin: Patriot, S-400, Precision Strike Missile, each name hinting at the system's strength or nation of origin. By the end of this phase, a full design blueprint emerges. It includes propulsion systems, warhead configurations, guidance electronics, and how it all fits into a mobile or stationary launcher. But a plan is only a plan. Now it needs to be built. Raw materials and manufacturing. Once the blueprint is approved, the spotlight shifts to the factories, the places where metal meets purpose. A missile isn't just a tube with explosives. It's a combination of specialty materials, complex electronics, and exact manufacturing. Engineers begin by sourcing high-strength alloys and carbon composites. These materials must survive intense heat, pressure, and impact, all while staying light enough to fly thousands of kilometers. Machinists carve precision components using CNC lathes and robotic arms. Tolerances are tight, often within fractions of a millimeter. One error in the motor casing or guidance shell could mean mission failure. In another section of the facility, technicians prepare the solid fuel propellant. This is a delicate process. Fuel and oxidizer are blended, poured into molds, and cured like a hardened gel inside the missile motor tube. Once set, this mixture becomes the engine's heart. At different stations, the missile's body comes together in sections: the warhead, guidance system, engine, and fins. Each section goes through rigorous quality checks. Engineers scan parts using X-ray systems to detect micro cracks. Propellant is analyzed for burn consistency. Wiring and electronics are tested for shock resistance. The goal is simple: nothing can go wrong after launch. By the end, what began as blueprint lines on a screen becomes a real missile, built, tested, and ready for the next phase, making it flying. Solid fuel rocket motors. The real power of a missile comes from what's buried deep inside: the solid fuel rocket motor. This is the system's engine, and it's built for speed, strength, and reliability. The process starts with an ignition system. Once triggered, it sets off a chemical chain reaction in the propellant core, where fuel and oxidizer burn together. What happens next is raw, explosive science. Superheated gases form and expand rapidly inside the combustion chamber. That gas pressure builds quickly and looks for an escape. It finds it through the nozzle at the back, specially designed to channel and accelerate the gases. As the gases exit, they create thrust in the opposite direction, propelling the missile forward. This is Newton's third law in action. Every action has an equal and opposite reaction. The result? Speeds exceeding Mach 3 or about 2300 panorama. But it's not just about power, it's about control. The nozzle must withstand high heat, and the motor casing must hold massive internal pressure without rupture. Engineers use simulations and real-world testing to ensure performance. Motors are test-fired in controlled chambers with every aspect: burn rate, gas temperature, thrust curve, recorded and analyzed. All of this happens in a compact tube. No moving parts, no turbo pumps. It's simple in appearance, but in reality, it's one of the most demanding pieces of engineering in the defense world. Solid fuel motors don't need maintenance, don't need external fuel systems, and can stay ready for years, making them perfect for rapid deployment and battlefield readiness. Guidance and navigation systems. Making a missile fly fast is easy. Making it hit the right target at the right time, that's where the guidance system comes in. Today's advanced missiles use a dual guidance setup, combining inertial measurement units, IMUs, with military-grade GPS. Together, they ensure accuracy even under pressure. Let's break it down. GPS works by connecting to satellites, triangulating position in real time. That's great until the signal is jammed or blocked. That's where inertial navigation comes in. Using onboard sensors like gyros and accelerometers, it tracks every change in direction and speed, constantly calculating in position without needing external input. Even if the missile flies through a tunnel, canyon, or radar-jammed battlefield, it knows where it is. This guidance system is paired with a flight control mechanism, small fins or vanes that move based on electronic commands. If the missile drifts off course by even a few meters, the fins adjust in real time, redirecting it. These adjustments happen fast, within milliseconds, and continue throughout the flight. It's a delicate dance between two systems, but the result is impressive. Whether it's flying 50 kilometers or 500, the missile can stay locked onto a moving or stationary target, even as conditions change. This tech ensures that one launch equals one hit, a critical factor in modern warfare, where every shot must count. Warheads and payload options. At the end of the missile's flight is its purpose, the payload. This is the part that does the real damage, and designers tailor it to the mission. The most common type is the unitary warhead, like the WD-18. It delivers a single, powerful blast, equivalent to 500 pounds of TNT, used to destroy bunkers, radar stations, or large vehicles. Then there are cluster munitions, which break apart mid-air, releasing hundreds of smaller submunitions. These are effective against troop concentrations, light armor, or supply convoys. Some missiles carry as many as 950 bomblets, spreading destruction over a wide area. There are also precision strike payloads, designed with fragment-forming casings to target specific equipment, radars, launchers, or air defense systems. What's clever is the modular design. Missiles can be fitted with different warheads depending on mission type. Swapping out payloads doesn't require a full redesign, just different loading at the base. And when the missile hits its target, an impact sensor inside triggers the explosion at the optimal moment, either on impact, in the air, or a split second before. This flexibility is what gives modern missile systems their power. One launcher, multiple missions, one missile system, countless strategies. Size, speed, and performance comparison. To really appreciate what these missile systems can do, you have to grasp the scale, not just their size, but their sheer speed and performance range. Imagine standing next to one. These missiles are about 13 feet long, with a diameter roughly the width of an average car tire, just under 2 feet. They weigh in at around 560 kilograms, or over 1,200 pounds. Now picture that mass tearing through the air at Mach 3, that's about 2,300 miles per hour, nearly 3 times the speed of sound. That kind of speed isn't just impressive, it's tactical. A missile moving that fast gives enemy systems little time to react. Compare that to other well-known missiles like the French-British Storm Shadow, which cruises at around 600 miles per hour, or the Russian KH-101, which tops out at roughly the same. Those are still fast, but when you stack them next to a Mach 3 performer, oh, the gap is clear. It's not just about outrunning defenses, it's about hitting before the target knows it's been seen. But size and speed aren't the only story. These missiles are designed to operate from a wide range of launch platforms, from high-mobility wheeled systems like HIMARS to heavier track-based platforms like the M270 MLRS. That adaptability means one missile type can serve multiple missions. Rolled off a cargo plane one day, fired from an armored vehicle the next. It's flexibility on a strategic scale. And when you compare these weapons side by side, the engineering becomes even more impressive. Each missile is compact but deadly, optimized for maximum efficiency in flight and payload delivery. This isn't just brute force design, it's precision built into velocity. From the way it launches to the way it corrects its path mid-air to how it strikes its target, every part is finely tuned for performance. This combination, speed, scale, flexibility, is what makes modern missile systems so powerful. It's not just about hitting a target, it's about doing it faster, farther, and smarter than anything else on the battlefield. Launch platforms and mobility. A missile is only as effective as the system that gets it into the fight. That's where launch platforms come in, and mobility becomes mission critical. Today's missile defense systems are no longer static emplacements. They're on wheels, on tracks, in the sky, and they move with purpose. The U.S. military uses two key platforms: HIMARS, which is light and wheeled, and MLRS, which is heavier and tracked. Each brings its own advantages to the battlefield. HIMARS can be deployed quickly. It's light enough to be carried in a C-5 Galaxy aircraft, rolled off the plane, and made operational within minutes. That's game-changing when time and location are the difference between success and vulnerability. Meanwhile, the MLRS system brings more firepower with its dual pod launcher, capable of deploying twice as many missiles. It's slower, yes, but it thrives in rugged terrain where mobility and off-road capability count. Inside the vehicle, the setup is efficient. HIMARS can be operated by a single soldier, while MLRS typically uses a three-person crew, driver, gunner, and commander. Despite the numbers, both platforms use computer-assisted systems that simplify the loading, aiming, and firing process. This means fewer people, faster response, and less room for error. Once deployed, these platforms use a tactic called shoot and scoot. That means they fire and then move immediately before the enemy can locate and return fire. It's a strategy that greatly increases survivability, especially in high-threat environments. Reloading is fast, too. A reloader vehicle with a mechanical arm can switch out pods in just minutes, keeping the crew out of danger and the system ready to fire again. These launch platforms are more than just vehicles. They're the muscle behind the missile. They turn a powerful weapon into a mobile strike unit capable of delivering precise, high-speed firepower from virtually anywhere. In modern warfare, that kind of flexibility is everything. It means these systems can strike fast, hit hard, and disappear before the enemy even knows what happened. Launch sequence and fire control. Once the missile is loaded, the real choreography begins. This isn't just pushing a button, it's a coordinated process powered by tech, timing, and tactical awareness. It starts at the command center, where intelligence teams assess threats and assign targets. When confirmed, the command flows to the launcher crew. Before launch, systems run diagnostics. Everything is checked: circuits, GPU, weather, communications. Any fault could cause to failure. Once systems are green, targeting software loads GPS coordinates or real-time radar data into the missile's brain. At launch, a small ignition charge lights the solid fuel propellant. In less than a second, the missile is airborne. Pure acceleration. It's not flying blind. The missile updates its path constantly, adjusting course via GPS or, if jammed, switching to inertial navigation. Fins unfold mid-flight, steering it with precise corrections. As it nears the target, the terminal phase begins. Onboard sensors lock onto the final objective, whether radar, launcher, or vehicle. Once locked, the warhead arms. At the perfect moment, a sensor triggers detonation, on contact or just before, based on payload type. From command to impact, it all happens in under a minute. This is what makes modern missile systems so deadly: fast, smart, and surgical. The enemy gets no warning, no chance to react. Patriot SAM System, dissecting its core. The Patriot missile system isn't one machine. It's a network designed to detect, track, and destroy airborne threats with precision. It's built around 6 core parts: the engagement station, power plant, radar, antenna mast, launcher, and the missile. The engagement station is the command hub. Operators sit inside watching screens, analyzing threats, and launching missiles, controlling up to 8 launchers at once. The power plant uses diesel turbines to generate 150 kilowatts, feeding power to radar and controls, even in remote zones. The radar is a phased array, electronically sweeping the sky from a fixed 67.5-degree angle without moving parts. It tracks multiple threats from hundreds of kilometers away. The antenna mast enables long-range communication. The launcher itself holds 4 missiles in sealed pods, ready to fire. And the missile? It's packed with tech. Inertial sensors, jeeps, terminal seekers, and tiny thrusters that fire just before impact. It follows radar guidance but adjusts itself mid-flight, making it highly autonomous in its final moments. Together, these parts form one of the most trusted missile shields ever built. The Patriot system remains a benchmark, responsive, accurate, and ready for action. Patriot firing procedure. Seeing the Patriot system in action is like watching a well-rehearsed orchestra, except every note is about survival. When threats are detected, be it an incoming missile or a high-speed aircraft, the radar scans the horizon using overlapping radar beams, constantly sweeping the sky. These beams are so narrow and precise that they can lock onto a target in a cluttered or chaotic environment, isolating what matters from the noise. Once a target is detected, data is sent instantly to the engagement control station. Their operators, assisted by AI, analyze the incoming object. Is it a missile, a decoy? Is it heading for a city or a military base? Once confirmed as hostile, the system assigns a launcher to engage. Depending on protocol, the system may automatically decide to fire 2 missiles at one target, increasing the chance of a hit. Launch is rapid. The missile exits the canister, powered by a solid fuel motor. It begins its flight under inertial guidance, receiving corrections from the control station. But as it nears the target, it switches to terminal guidance, using a K-band seeker to fine-tune its approach. If necessary, small explosive thrusters adjust its path in microseconds. Finally, when the intercept point is reached, the Patriot delivers a hit-to-kill strike, literally colliding with the target. This isn't an explosion, it's body-to-body contact, releasing enormous kinetic energy. It's enough to destroy incoming ballistic missiles, cruise missiles, or aircraft. Once the threat is neutralized, remaining interceptors are disabled to prevent unnecessary launches. The Patriot firing sequence is built for speed and accuracy. In just a few seconds, from detection to detonation, it can stop what might have otherwise caused massive destruction. That's the value of integrated defense. No guesswork, no delay, just action when it's needed most. Comparing Patriot versus S-400. As we examine global missile defense systems, 2 names often rise to the top, Patriot and S-400. Each reflects the engineering priorities of its origin. One American, the other Russian. Both are powerful, but their design philosophies are starkly different. The Patriot system uses a centralized radar and command setup, integrating detection, tracking, and engagement all in one structure. The S-400, on the other hand, splits these tasks across multiple radars, long-range, all-altitude fire control, creating a more distributed defense web. Deployment speed is another key contrast. The S-400 can reportedly be operational in as little as 5 minutes, while the Patriot may take 25 minutes or more to fully activate. That difference could matter in a surprise attack scenario. Then there's the cost. A single Patriot missile can exceed $4 million, while the system itself can cost upwards of $1 billion per battery. The S-400 offers a lower price tag, around $500 million per battery, though its export versions may lack key capabilities. Despite these differences, both systems can detect and destroy high-speed threats and work alongside aircraft and satellite tracking systems. Their roles aren't just to intercept, they act as deterrents. Choosing between them often comes down to political alliances, budget, and battlefield doctrine. In the end, it's not always about which is better, it's about which system fits the fight. Next-gen precision strike missiles. If the Patriot and S-400 represent current missile defense, the next generation is already moving forward. Enter precision strike missiles, engineered for tighter accuracy, longer reach, and smarter targeting. These missiles are slimmer but deadlier, with longer airframes, lighter profiles, and custom-designed payloads that maximize blast effect with surgical precision. What makes these missiles different is their flexibility mid-flight. Some use waypoints to fly to one location, adjust trajectory, and then strike another, hitting a staging area before eliminating a radar site. They can be launched in rapid pairs to confuse defenses or overwhelm radar systems. And thanks to modular internal bays, future versions might carry multi-warhead payloads or even plug in AI processors that adapt mid-mission. The hardware is paired with upgraded military GPS systems, hardened against jamming and spoofing, and the airframes are designed with space for future tech expansion, whether that's improved tracking, more efficient motors, or new warhead types. These missiles represent more than evolution. They're a shift in philosophy. It's no longer about overwhelming force alone. It's about pinpoint attacks with minimized collateral damage, executed at speeds and distances that change the rhythm of war. The battlefield of the future will rely on missiles that think, adapt, and strike with digital precision. Strategy, ethics, and future outlook. As missile systems grow more capable, a new question takes center stage. Not just how they work, but how they should be used. The power to hit a target across continents within minutes is no longer futuristic. It's today's reality. That power demands strategy, but also caution. Each missile launched carries not just explosives, but political consequences and ethical responsibility. On one side, advanced missiles reduce the need for manned missions, keeping soldiers out of harm's way. On the other, they risk increasing the temptation for preemptive strikes, especially when operated autonomously or controlled by remote AI systems. The debate is ongoing. Should machines decide when to kill? Who's accountable if a system malfunctions or misjudges? At the same time, nations race toward hypersonics, swarming drones, and AI-guided seekers, a future where missile systems may be faster, smarter, and harder to stop. Integration across air, land, and space is also growing. Defense networks are becoming global, with satellites, radars, and ground units talking in real time. And yet, amid all this tech, the core mission remains the same: protect lives, deter conflict, and maintain stability. As these systems evolve, they remind us that true strength isn't just about power. It's about using it wisely. The future of missile defense isn't just about precision. It's about judgment. From raw alloys to radar scans, every part of a missile defense system is a triumph of purpose-built design. As threats evolve, so too does the technology that shields us. If you enjoyed this deep dive, subscribe for more engineering insights. And remember, behind every launch is a story worth telling.